Hello everyone, welcome back to the course on materials informatics. In this lecture we will resume our discussion on regression. So just to give a brief recap of what we did in the last lecture, we defined our regression problem of interest. So we wanted to predict median house prices in California, the state of California, based on 1990 data. We defined some performance metrics, mainly root mean squared error and mean absolute error. We also looked at the differences that we get when we randomly split data into train and test set versus stratification of our data according to income categories when we split into train and test sets. We visualized the data, we understood some correlations such as how is income correlated with housing prices, number of rooms in a house, number of bedrooms, population, median age and so on. So there are various metrics that are available in our data set and we understood correlations among them and with the target variable. And we also tried introducing 3 new features and we saw how they were correlated with the target variable, which is our median house price, right. So in this lecture we will take this discussion forward. So we will start preparing the data that we have available for our machine learning exercise. So basically for doing our regression, so we will actually build some simple models as well. And just as a note, all the schematics that I will be using in this lecture are part of this textbook by Aurélien Geron, unless otherwise specified. Alright, let us now prepare our data for the machine learning exercise. So there are a couple of things that we need to do, right. So for example in our data set there is some missing data in this total bedrooms variable or feature, right. So all the other data points we had about 20,600 or so data points, but total bedrooms there are only about 20,400, so there are about 200 missing rows, right. So we need to do something about this feature. So there are different approaches that we could take. So one is we could simply add zeros, right, for all of the missing data points, right. We could add the mean values, so we could calculate the mean number of total bedrooms, right, and we could add that mean as a placeholder value for each of those missing instances. We could do the same thing with median, so we can calculate the median of the total bedrooms, so the median distribution of the total bedrooms feature, and we could add that median value in the missing data points, missing instances. So in this specific example we are going to add in the median, right, for the missing instances. Another sort of more radical approach, if you do not trust any missing data, you could also remove the instances completely, as long as it is not going to remove a majority of the data points associated with your data set. So that is another option, but in this exercise we will be looking at adding median values. So that is one preparation that we have to do to our data set. The second is there is one feature which is in the form of text rather than in numerical values, and that is how close a locality or a community is to the ocean, right. So we had various text attributes to them: less than 1 hour, near ocean, island, near bay, inland and so on, right. So we have 5 different categories, 5 different text categories. And machine learning as a tool is able to deal with numbers much better compared to text, at least the classical machine learning models. So we need to find a way to convert this text into numbers, and the strategy that we will be using is what is referred to as one-hot encoding, right. So basically we will convert this text attribute into 5 columns. So there are 5 different types of text that the feature can take, the location feature can take, and we for each of those features we will assign a value of 1 or 0 depending on which feature is actually occurring for that instance. So for example, if a locality has if a locality is situated inland, right, so there are 5 possible text features, 5 possible columns, right. So only the inland feature will have a value of 1, the remaining features, so less than 1 hour from the ocean, near bay, near island and so on, they will all have zeros as their values, right. So we will convert one text feature into 5 columns, right, and each of those columns will have binary values, so either 1 or 0. So this can be done in a fairly straightforward fashion. So this whole process of converting text into binary columnar values is referred to as one-hot encoding, and this can be done in a straightforward fashion using scikit-learn libraries, right. So this is what we will be doing in our exercise as well. And in the last lecture we looked at adding new features and how they can maybe improve our model, right. So because some of the features had better correlations than the features that came with the data set itself. So we will be adding those features using what are referred to as transformers. So transformers basically are a more systematic way of handling data using pandas data frames. You do not have to use transformers, but I am just demonstrating a cleaner way of adding new features. So you can also use pandas as input functions and input features to add in new features, but using transformers is just cleaner, more systematic way, right. So I will be demonstrating how to use transformers, and then once you start defining transformers, right, you can now collect a bunch of transformers and build pipelines, right. So the objective of a pipeline is you feed in some data, right, and then it goes through a series of transformations. So be it missing data, be it transformation of text data into numerical data, it could also be adding new features, and it could also be scaling, right. So standardization, normalization and so on. So you accumulate all of these mathematical operations into a pipeline. So any sort of data that you are dealing with in the future, so that could be a a materials related data set, right. So for example predicting formation energies for as a function of composition. So let us say you have a new data set, right, that comes in. Once you have built a pipeline, you can simply just pass the data set through these pipelines and your data will be transformed and will be ready to do machine learning, right. So we will see how to construct pipelines which are a collection of transformers. So let us go back to the notebook and then we will go through all these exercises. Alright, so in our notebook in the last class we looked at adding new features. So right now we are going to start with preparing the data for the machine learning algorithms. So the first thing that we have to do is the data cleaning step. So we have to add in the missing values in the total bedrooms feature, and we are going to do that by adding in the median values, right. So first step is to drop the sort of target values. So we do not want to touch the target value, which is our median house value, right. So that feature we do not want to touch when we are preparing the data for machine learning. So we are going to drop that and then sort of deal with the remaining data, right, that is there in our data set. So that is what we have done in this first cell here. So in the second cell we are going to use this sort of class called simple imputer, which is there readily available within scikit-learn, and with simple imputer you can put in various strategies. So you can add in median values, you can add in mean values for a given column, right. So we are going to choose the median value here. So let me create an instance of the imputer class, and then so I am just creating a imputer class there. We will get back to that imputer class in one of the subsequent cells. And the next thing I am going to do is that the imputer class only works on numerical data, it does not work on text data. So we have ocean proximity as our text feature, so I have to drop it. So let me drop that temporarily and create a new data frame called housing underscore num, so that only has numerical features, right. So the first thing that we have to do for the imputer to work, so for us to insert median values in total bedrooms, is to actually calculate the median for each column, and that is what this imputer.fit function does, right. And we can also get the statistics. So statistics basically gives us the mean values for each of the columns that we have considered, right. And we can also check whether these statistics are the same as what pandas calculated within its inbuilt functions like the describe function, right. So once we have the imputer defined, we can use this imputer.transform function. So what this transform function does is that for all the numerical features that it has identified, right, for whatever rows, so for whatever instances that numerical feature is missing, it is going to add in the imputed value, the median value, right. So that is what the transform function does, right. And once you have the transform function, basically the imputer.transform function only gives you an array, so it does not give you back the data frame object. So we take that value and then create the data frame again, right, so that we can go ahead with other operations, right. So we create the data frame again in this cell, and then just to check that the data frame looks fine, right, we see that you know we look at the first 5 rows of the data frame. Yeah. So that was the imputer, which basically ensures that the total bedrooms, so missing data, missing numerical data is taken care of. Now the second thing is dealing with the text data, so that we have to change to one hot encoding, right. So we once again we isolate the text category here, so which is referred to as ocean proximity, right, and ocean proximity has different values, right. So it has less than 1 hour, near ocean, inland, and there is also near bay as the different values. So for doing one hot encoding, there is once again a standard class that is available in scikit-learn called one hot encoder. So let us create an instance of the one hot encoder, and then once we have created the one hot encoder, we can then use the fit transform function here, right, to both fit our data. So we have 5 different you know text types that we have, right. So the fit function basically you know identifies these 5 types, and the transform function basically changes this one column text data into 5 columns of one hot encoded data. So you have ones and zeros depending on whichever text value was assigned for that specific data point, right. So the fit transform function does it in one step. So in the case of the imputer function, we used a fit function and a transform function later. The fit transform is you know does everything in one go, and it returns us a sparse matrix. So it is not, again it is not a data frame object, it gives us a sort of a numpy matrix type of object, and it typically returns a sparse matrix. Now there are differences between what a sparse matrix is and what a dense matrix is, we will not get into the details, but by default scikit-learn will give us sparse matrix which are actually easier to handle, so they are faster whenever we do matrix operations, right. So we will stick to the default settings for now. And just to get a sense of whether the one hot encoder got all the categories correct, got all the text categories correct, we can print the categories, which is what is being done here. So you see that here there are 5 different values, right. So there is less than 1 hour from the ocean, inland, island, near bay and near ocean, right. So it has indeed identified all the 5 different text objects and it has correctly transformed them into this one hot encoded vector. Okay. So now that we have understood how to do imputing, so how to add median values and how to do one hot encoding, let us now look at how to add new features with custom transformers, right. So we are going to define a new class here. I know for those of you who are new to Python, this may be quite a bit of content to take in, but just go with the flow for now, right. So we are going to basically create a new class that defines certain set of mathematical operations, and then we are going to create an instance of this class which allows us to systematically add in new features however we want it, right. So for creating this custom transformers, basically we need to import a few classes from scikit-learn. So that is from the scikit-learn base library, which we have done it, and then I am going to define a class called combine attributes adder. Right. So it's basically it's a class that is meant for combining different attributes, creating new attributes and then adding them to the data frame. That is what this class is supposed to do, and the attributes that we are going to try to add are bedrooms per room, right. So this is one attribute that we had introduced or one feature that we had introduced in the last lecture to be quite useful. The second one is rooms per household, right, and the third one is population per household, right. So we have defined these 3 as our new features that we are going to calculate on the fly and then add it to the data frame. So we are just doing that in a systematic fashion by defining this class, right. And then once we have defined this class, right, and then we define some functions that this class is capable of. So we have defined a fit function and we have also defined a transform function, right. So once that is done, then we can create an instance of the class, right, and then we can do this, we can call this transform function which is going to transform our data set and add these new variables, add these new features, right. So we have already called that and created an instance and called the transform function. So let us see whether everything worked correctly. So if you now look at your new transformed housing data set, you now see that 2 new attributes have been added, the rooms per household and population per household. Now you may be wondering why didn't we add bedrooms per room. I mean, that's just for demonstration, because when we created an instance of the class combine attributes adder here, we said add bedrooms per room is false. So basically that attribute or that feature is not going to get added, right, but we can always turn it to 2, and then it's going to add the bedrooms per room as a new feature to the data frame, right. So everything seems to have worked fine, so we have added the features, right, the new features. Okay. So we have now understood how to do imputing, how to do one-hot encoding, and how to systematically add in new features using custom transformers. Now let's put everything together in a pipeline, right. So we are going to create what is referred to as a pipeline here, and pipelines are classes that are available from scikit-learn, right. And in addition to the 3 operations that I mentioned, so adding in medians, median values, one-hot encoding, and adding in new features, we are also going to scale all the features, all the features within our data set. We are not going to test the target values, only the features, right, the attributes. So all the features we are going to scale them in a standardized fashion. So we are not going to do normalization, we are going to do standardization, right. So that is what the standard scaler class does within scikit-learn.preprocessing package, right. Now let us see how to define this pipeline, right. So I am going to define something called a numerical pipeline, that is why it is called num pipeline, right, and the pipeline does 3 things. So it is going to do impute, right. So I just have to pass in simple imputer as one of the arguments, right, and then I am going to add new attributes. So that is combine attributes adder here, and I am going to add in the scalar transformer, which is going to do the standardization process for me, right. So all I have to do is create an instance of this pipeline, create an object of this pipeline class, and then call this fit transform function. So for all pipeline classes there will be a fit transform function which takes in a class, does all the operations that you have mentioned in a sequential fashion. So it will do imputing first and then add in the new attributes, and then it will do the standardization. So it will do all the processes in a sequential fashion, and then it will return back your transformed data set, once again in the form of an array, not really a data frame, right. So if you want to once again get back the data frame, you have to reinitialize the data frame, right, but it does give you the transformed data set in the form of an array, right. And we have already executed this cell here, and you see that you have this transformed data set now available here, right. So we only did imputing, attribute addition and scaling, we have not done the one-hot encoding, right. So that also can be introduced as a pipeline, and in general it is a good exercise to handle numerical features or numerical attributes separately from text attributes. So typically text attributes are also called categorical attributes. Typically it's better to treat both of them separately, so have separate set of transformers and even separate sets of pipelines, and you can build one common pipeline which integrates these 2 different pipelines. So one pipeline for numerical features and another pipeline for text or categorical features. So that is what we are going to do here, right. So we created a numerical pipeline, now we are going to create a pipeline for text categories, and that is a fairly simple pipeline in this case. We are just going to call the one-hot encoding transformer. So we are going to perform one-hot encoding and then put it into our transformed data set. So let me execute this cell. So here I'm calling this transformer called column transformer here, right, and column transformer is a way for me to sort of add in both my numerical pipelines as well as categorical pipelines, text pipelines. So for my categorical features, I define what is my categorical feature, my text feature, which is ocean proximity here, right, and for those categorical features I am just going to call the one-hot encoding here, right. So my full pipeline basically has my numerical pipeline which I have already defined in the previous cell, right. So that does the median, adding attributes and standardization, and then my one-hot encoding which is my text transformation, right. So I have combined both the pipelines into a single full pipeline, and I have created an instance of this pipeline class, right. Once I have created an instance of the pipeline class, I once again call this fit transform function, So fit transform is quite common whenever you are preparing data, right. So you would almost always have functions that have fit underscore transform or fit and transform as two different functions. So you once again call the fit transform function on your original data set, right, and it's going to give you your fully prepared data set that is now ready for machine learning, right. So you are getting the housing prepared data set here, and any so by default assume that whenever you call a fit transform or a transform function, you won't get back your data frame. Typically you will get back a numpy array, and that's what we get here also. So if required we will convert this back to a pandas data frame, but for most of our machine learning models we can actually deal with numpy arrays themselves. So using numpy arrays is also certainly fine, right. So we have now prepared our data set fully, and that is stored in this housing underscore prepared array, right. And just to understand that we have gotten all the dimensions correct, so we can sort of print the shape of this transform data set. So remember that we had about 20,600 total data points, and we have split that into training and test set. So the test set has about 4,000 data points, right, 20%. So the training set has about 16,000 data points, so that seems to be correct. So there are 16,000 rows, and there are 16 columns. So the 16 columns also includes the one hot encoding column, so those are 5 columns, right, and you have the 3 new attributes or features that you added. So there are 8 new columns that have been added into your data frame here. So that's why you have more columns than you had at the starting of this exercise. Okay, let's now go back to our slides and look at how to train models now. Okay, so for fitting any model, especially using scikit-learn, so whenever we consider simple functions, simple machine learning models, we have to use this function called fit, right. So the fit typically takes in 2 attributes or 2 features. So one is your x is basically your set of features that you have, so it can be a numpy array, and y is your target variables or your target labels, right. So this also can be a numpy array, right. So you simply call fit of x comma y and your model has been fit already. So that's very simple to actually fit models in scikit-learn. Right now we will explore a simple linear regression model and a simple decision tree model, right, and we will see how these 2 models perform. So if we want to just examine how well the model are doing within our training set itself, so training set the model has actually seen all the data points, but we will still need to see how good the model is, right, on the data points that it has seen. So for doing that we can use the predict function. So we can pass in a subset of our training data within this predict function to see what the model is actually predicting for all the data points that it has seen already, right. So this is often used to examine how good a fit is for the model. We will also do the evaluation metrics, so the root mean square errors and the mean absolute errors. So let's get back to the notebook and do these exercises. Alright, so let's try to fit some models here. So first of all let's try to fit a simple linear regression model. Again, linear regression model is fairly simple, so you just import linear regression from scikit-learn .linear model package, and then create an instance of linear regression class itself. So you create an object of it, and then you just call the fit function. So in the fit function the first argument is the x variable, all the features, so we are going to pass in the housing underscore prepared, which has all the transformed features that we wanted for our data set, and housing underscore labels is our target values, it's our median prices, so that's the target values that we are going to fit, so that's our y, right. So and we have already executed this cell, so the linear regression model is done, it's actually fit. So as you can see many of the classical models can be fit very quickly with scikit-learn, right. Let's now see how good these fits are, right. So we are going to take some the first 5 data points, right, from our original data set here, and then just so that we are comparing apples to apples, we sort of pass the selected data into our pipeline, so into our we do all the regular transformations, right, and then we make predictions, right. We make predictions, and the following are the predictions and the actual labels, right, and you see that the predictions are okay. I mean it's not a terrific model, but you see that the first data point for example is 210,000, you are predicting about 280,000, so that's off by about $70,000, not a small amount, but in the grand scheme of things this may still be a reasonable error, right. Similarly the second data point, the actual value is about 317,000 and you get about 340,000, the third one is 210, 196, 59,000, 46,000, 189, 254. So probably the last data point has the largest error I would say, but in general I mean the model seems to do okay. It's not a great model of course, but it seems to do okay. But that's just looking at 5 data points, and we have 16,000 data points in our training set. So let's get an overall sense of how well the model is doing by calculating our metrics, right. And to calculate metrics once again you have standard functions that are available in scikit-learn. So we can import mean squared error as a function, and then we take a square root of it to get the root mean squared error, and similarly you can also call in the function for mean absolute error. So let's execute or call the mean squared error function now. And the last line basically takes the square root, so we are actually printing out the root mean squared error here, and it looks like the root mean squared error is quite high, right. So we have an error of about $68,000 with our model, and this is actually a significant error, right. I mean there are entire houses that are going to cost maybe $50,000, $40,000 according to 1990 data of course. So we are off by the entire cost of some houses, right. So again this is not a great model, but it's useful to know these metrics. Let's also calculate mean absolute error. Let's see if mean absolute error also tells us our model is not that great. So we calculate mean absolute error, and yeah it says it's about $50,000 off, 49,439 here, right. So these are large errors. Ideally we would like our model to do better than this, right. So let's now explore a slightly different model. So linear regression, we will look at all these models little more in detail in the upcoming lectures, but linear regression is a fairly simple model. So a decision tree is a slightly more complex model, so it has more sort of variables that it can fit to, so more weight terms that it can fit to, and hence maybe it will do a better job compared to linear regression, right. So let's try out decision tree. And to again create a decision tree model, it's a fairly simple straightforward exercise, just like linear regression. You create an instance of decision tree and then you call the fit function, right. So for decision tree we have to give a random state, because depending on what the random state is you can have different fits that are generated. So for reproducibility we will use a random state of 42, right, and so as you can see the model fit very quickly, right. And let's see how the predictions are, and it looks like decision tree is a perfect model, right. So we get 0 errors on our root mean squared error metric, so looks like it's almost a perfect model. So do we need to do any more? Probably yes. So in machine learning there is never something called a perfect model. So whenever you get an absolute error of 0, so be it root mean squared error, be it mean absolute error of 0, usually something is going wrong. And the thing that could be going wrong is the model could be overfit, right, or you have some variable declaration problems or calculation problems in your Python notebook that you would have to actually debug. In our case it's probably overfitting, so the model is overfitting, so we need to evaluate the model slightly differently using some other metrics, and that's what we will cover in our next few slides. So let's get back to the slides. Okay, so as we saw our decision tree model was almost a perfect model, but it's sort of perfect because it has overfit on our training data, and the way to evaluate whether our model has overfit or not is to do validation checks, and specifically we will put our models through this cross validation exercise. So what is cross validation, right? So if you consider k-fold cross validation, what it basically does is it takes your training data set, splits that into k different folds or k different subsets, right. It trains on all the k-1 pieces of your data set and then evaluates your model. So the last piece of large subset of data has not been exposed to your model, and then your model gets evaluated on the last piece of data, right. So you do this once and then you repeat it with your second data set. So initially you took let's say it's a 5-fold cross validation, right. So k is an integer here. If it's 5-fold cross validation, you split your data set into 5 subsets, right. Initially you train on the first 4, evaluate on the 5th one, right. In the second exercise you train on 2, 3, 4 and 5 and then you evaluate on your first set. In the third instance you could train it on 1, 3, 4 and 5 and evaluate on your second subset and so on. So you see that you have at least 5 different models that you can actually create, that you can actually train, and you take an average score over all of your 5 different models that you have trained, right. So if you do k-fold cross validation, you get k models and you get k error metrics, and you see on an average how your model is performing across these k different subsets of your model, subsets of your data, right. So that is what is being written here. So you split your training set into k folds, train on k minus 1 folds and validate on the remaining fold and repeat this k times, right. And you take the average score. The scoring metric is typically mean squared error, but you can use other metrics also, right. And for this cross validation exercise we will try out random forest. So this model is more complex than our decision tree model. We will cover random forest a little later in the course, and we will also try out support vector machines. Support vector machines are really good models. They are less in complexity compared to random forest, but it is useful to compare. So one thing to note is that k-fold cross validation can become quite slow in large data sets and very complicated models. So we will have to include other strategies to ensure that our models do not overfit, right. But we will get to those strategies later. For simple classical sort of machine learning models, k-fold cross validation is usually good, right. So let us get back to our notebook and do this cross validation exercises. Okay, I am just going to evaluate a few of the cells because they may take time. So in the first cell what I am basically doing is I am importing this function called cross validation score, right, and I am basically passing my decision tree model here, that is my tree underscore reg model here, and I basically say okay, you capture the negative mean squared error for my decision tree model over 10 subsets of data. So I am doing 10-fold cross validation here. And I am printing and I am storing all the scores in tree RMSE scores, right. And then I define a simple function to display basically all the scores and also some statistics. So the scores themselves, the mean and the standard deviation. So you see that the scores are distributed over range, you have a mean value and then you have a standard deviation value. So previously our decision tree was a perfect model, right. So it had 0 root mean squared error on our entire training data set, but if we do cross validation now, 10-fold cross validation, we see that the mean error on the 10 different subsets of the data is about $70,000. So it's in fact doing worse compared to our linear regression model, right. So this is a clear instance that the model has overfit, right. And if we do the same exercise for linear regression, right, we see that the mean value is slightly better than decision tree, right. So it has a mean value of about 69,000, right, and a standard deviation of about $2,000. So the linear regression also is not doing that great, but it is definitely doing better than our decision tree model. So our decision tree model was clearly overfit, right. Let us now do this exercise for our random forest, right, random forest and support vector machines. So for random forest once again, let me execute a few of the cells because random forest can take some time, right. So for random forest you can sort of create an instance of the model from the scikit-learn ensemble package, right. The syntax is the same, you create an instance. The number of estimators is an important hyperparameter in random forest. We will see how to tune the hyperparameters a little later, and of course you need to mention a random state as well for this model. And once you have created an instance you just fit, right. So fitting is straightforward, and we get some predictions on the random forest on our training set itself. So we simply pass in all the features of our training set and then we use this predict function, right. So we are asking random forest model to make predictions on the data set that it has already seen, right, and we can now compare that with the true values and we can evaluate our error matrix, which is what we are doing here, right. So we are evaluating the errors between the true values and the predicted values here, and it looks like the random forest has a root mean squared error of around $18,000. So on the surface it is doing better than both linear regression as well as decision tree, right. But again the key is examining cross validation, right, because again random forest is a complex model, more complex than decision tree itself, so it could have also overfit, right. So in the next cell we are basically doing cross validation, and of course you see that the cross validation is taking more time than normal than decision tree models, for example. So in general the more folds you have in your data set, so if you have 10 fold cross validation, you have to train 10 models, so that takes more time than if you do 5-fold cross validation where you train only 5 models, right. So once the cross validation comes up, we can examine this course. Yeah, so the cross validation is done, and we see that random forest is marginally better than both linear regression and decision tree. It gets a mean error across the 10 folds of data of about $50,000, right. So linear regression was about 69,000 and decision tree was about 71,000. So random forest seems to be doing better than both our linear regression and our decision tree models, even upon validation. Okay. So we can also get some statistics of sort of random forest using data frames. So we can create data frames on the fly based on all the different cross validated models, and we can also get some statistics on the fly. So the next cells, so cell number 65 here basically does that, right. So it creates a data frame on the fly and then it evaluates its statistics. It creates a data series on the fly, not a data frame, and then it creates statistics, right. So it creates how many data points you have. So we have 10 models, so count as 10, what is the mean value, standard deviation, and so on, right. Okay. So let us now build a support vector machine regression model as well. Once again the syntax is simple, you just import the SVR model, right, and SVM stands for support vector machine package within scikit-learn. So the syntax is once again straightforward, so you use the fit function, right, and once the model is fit, we then get the predicted values on the data points that the model has already seen, right. We evaluate the error using mean squared error, and then we take the square root to get the root mean squared error, and we see that the root mean squared error is quite high, right. So support vector machine regression has an error of about $111,000 on the entire data set. So this is actually even higher compared to our linear regression and decision trees, right. So support vector regression is clearly not working that well in our data set, in our housing data set here. So the next step is fine tuning our model. So let us go back to our slides. Yeah. So for fine tuning the model, the important aspect is to get optimal hyperparameters, right. So each model will have its own set of optimal hyperparameters, and we will cover hyperparameters a little bit more in detail as we go along in the course. And the model performance can be tuned, so models can be made better by ensuring that you get optimal hyperparameters. And the most straightforward way to get these optimal hyperparameters is doing what is referred to as grid search cross validation. Give me a minute. Yeah, so grid search cross validation. So what we do in grid search is basically, let's say we have two different hyperparameters here, we create discrete set of values for hyperparameter 1 and another discrete set of values for hyperparameter 2, and we basically sample all the different combinations possible, right. So if we have 5 different values of hyperparameter 2 and 5 different values of hyperparameter 1, we basically create 25 models, right, containing different combinations of these hyperparameters, and we try to identify which model is the best based on mean absolute error, root mean squared error, and so on, right. Now hyperparameters can be quite sensitive, right. I mean your model performance can change quite dramatically depending on the kinds of hyperparameters you use. The usual rule of thumb is you typically vary by about 1 order of magnitude, observe differences, and then see what your scale should be, right. So should you vary your hyperparameter by 10, 100,000 and so on, or should you vary it by 1, 3, 5 and so on, right. So you have to do some tests, trial runs, and then we can sort of come up with how we are going to vary our hyperparameters. So we will fine tune our model, fine tune our random forest model. So let us get back to our notebook and use this grid search CV. Okay. So doing the grid search CV, there is once again a standard class that is available within scikit-learn. So it's under scikit-learn model selection, right. So in order to do grid search CV, we have to define our grid, right. So what are the hyperparameter values that we are going to scan, and that's what we are doing here. So for our random forest, the number of estimators, n estimators is a very important hyperparameter. So we are defining sort of 3 different values here, right. And also max features is another important sort of hyperparameter, and we are defining 4 different values there. So that's one set of hyperparameters. The other set of hyperparameters is n estimators and max features, but with another hyperparameter called bootstrap set to false, right. Now all of this might sound Greek and Latin to you, but bear with me for now. We will introduce and talk about these hyperparameters a bit more in detail when we discuss random forest models themselves, right. And then you create an instance of the random forest model. When you create the instance, you don't specify the hyperparameters because we are going to change the hyperparameters, right. So that's why this grid search CV is useful. And then you do the grid search, right. So you call this grid search CV class, you create an instance of it, you pass in the random forest regression, that's your model, and then your grid of parameters that you want to capture, to calculate. How much cross validation do you have, do you need, so we will say 5-fold cross validation. So for each combination of hyperparameters, we are going to get 5 models, right. So and then capture the average score across those 5 models, right. And that scoring is going to be the mean squared error. So here it is negative mean squared error because the way the model is constructed is a little different. So if you have models that have minimization of their objective functions, then you minimize mean squared errors, but if they have a maximization as an objective, then you maximize negative mean squared errors, right. And then you want to see the training score, so that's why we say return training score is true. So and then we basically fit our grid search. So we call the fit function and then pass in the x and y values here. So for the x and y values that you have fit, and for each hyperparameter combination, you are going to train 5 different models, right, and take the average mean squared error and then compare the average mean squared error across the different combinations of hyperparameters, and then you choose the optimal hyperparameter. So this, as you can see, this involves a lot of model training, right. So if you are doing this exercise along with watching this video, these cells can take quite a bit of time to execute. So you may have to wait a few minutes for them to actually give out the results, right. So for instance, if you look at our first set of hyperparameters, right, so we have 3 estimators and 4 max features, so that's 12 models, and then for that's 12 combinations of hyperparameters, and for each combination we are training 5 different models, so 5 different random forest models, so we are basically training 60 models. So that can take quite a bit of load, right. So luckily for us, I have already executed these cells, so you can see the outputs here, and the cell below here, the best parameters basically gives you what is the best set of parameters among those that we gave to the grid search, and it thinks that if you use max features as 8 and number of estimators as 30, that's your best, right. In order to get the best model with the best set of hyperparameters, you don't have to retrain the model again. You can just call it with grid search best estimator, right. So the best estimator returns back the instance of the model with the optimal set of hyperparameters. So you don't have to retrain the model with the same hyperparameters, that's already there. Right. Now let's look at some of the cross validation scores. So we see for all the possible combinations of hyperparameters, we see the cross validation scores being listed. So these are the cross validated mean absolute errors, right. Cross validated root mean squared errors, not mean absolute errors, right. And we will see that for the best estimator that we have, max features 8 and number of estimators 30, we have the lowest error, right, about $49,000. Okay. We can also create a data frame of these results just to get some statistics just for ease of visualization, and that's what we do here. So that's on grid search cross validation. We can also find optimal set of hyperparameters using a randomized search of hyperparameter values. So instead of doing a grid search, so as you can see, if you give 3 by 4 grid points, right, and give a cross validation of 5, you have to create 60 models, right. Now 60 models on 16,000 data points may be doable on a laptop, but if you now start scaling, so let's say you have 1 million data points or 10 million data points, and if you have to create, if you have more hyperparameters to scan, let's say you have 100 different combinations of hyperparameters, then you see that the model, the computational cost quickly scales up, and to avoid that, especially in very complex models, we can do what is referred to as randomized search. So you give for each of the hyperparameters that are of interest to you, you give a minimum and a maximum value, right, so basically a range of values, right, and the randomized search algorithm will at random pick combinations of hyperparameters, and hopefully it will try to arrive at the optimal set of hyperparameters. So the trick that most people do is they typically use randomized search for getting a rough sense of which combination of hyperparameters are good, and then go towards that locally best set of hyperparameters, and then you can do a finer grid search there, right. But just to give you a demonstration of how randomized search works, so we can once again from scikit-learn model selection, we can choose randomized search CV as our class. Once again, for random forest we have two important hyperparameters, so number of estimators and max features. So we are basically giving what is the lower value and what is the higher value, right, and then we create an instance of the random forest model, and then we pass it into the randomized search CV class. So you pass in the random forest model, what is the distribution of parameters, that hyperparameters that you want to look at, how you want to score, again we are going to look at mean squared errors, right, and what is the CV. So basically we are going to look at cross validated score of 5-fold cross validation, right, so average of 5 models, and of course we also need to do a random state initialization, right, so we do that too. And once again you call it you use the fit function to call, and you see that the model has already built, and then if you now look at the best, so I have also listed, so the model has basically created, the random search has basically created 10 different models, so that is the number of iterations here, n iter equals 10, so it creates 10 different models or 10 different combinations of hyperparameters, and for each of those 10 combinations it has created 5-fold cross validation, so 5 different models, right. So it has basically constructed 50 models and then try to identify which is the optimal set of hyperparameters, right. So that is what we are trying to identify using this CV scores here, listed CV scores, and we see that I think it is this one, the first one that is the best. So max features of 7 and number of estimators as 180, that seems to give us the best performance, right. Okay, so let us now analyze a little bit more the models and their errors, right. So we take in the best model from our grid search, not the randomized search, from the grid search, and then we also look at feature importances, so how much each feature that we supply to our model are contributing to our final predictions, right. So this is one exercise that we can use to identify some important features. So for instance this feature here is more important than this feature here, right. Of course I have not labeled the features here, we can so these should correspond to the same column headings that you have in your data frame, right. So you can identify which feature is more important, which feature is less important to your model's predictions. So this is often used to analyze the data to examine how good, how can we improve our model even further, right. And then in terms of extra attributes, so let us say we add in the extra attributes, we can also see how important these attributes are, right. And if you look at the feature importances, rooms per household as sort of about 0.05, bedrooms per room is also 0.05, and population per household that's slightly higher in terms of importance, it's about 0.1, right. So these are useful to analyze how our models are basically fitting, right. Let us go back to our slides, and we have one final task left. So we have now fine tuned our models also, right. The task that is now remaining is to basically evaluate our model on the test set. So remember that the test set is something that the model has not seen so far, right. So it has seen 16,000 data points through cross validation, right, during training and optimization, but it has not seen a single data point from our test set, right. So then the final step is to evaluate our model and test it, and then examine is our model good enough or not, right. The steps with the evaluation of the test set is, as we prepared our data points, our features on the training set, we have to do the same pre-processing on our test set as well. So if there are missing data points, add the median values, text values, change them to one-hot encoding, and then attributes, if you want to add the attributes, add them, and then standardization, right. So these are 4 things that we need to do in our test set as well, and this is where pipelines really help us, right. So because we have already constructed the pipelines, we just need to take the test data set, put them through these pipelines, and our data is ready for evaluation, right. So since test set is something for evaluation, we will use only the predict function and not the fit function, because if you use the fit function then the model sees the data. So if you use the predict function, the model is only evaluated on the data, and then we will evaluate the metrics, the same metrics, root mean squared error, mean absolute error. We can also get an idea of what the confidence intervals are. So what is the error bar on our error values themselves, right. And then if finally we have to make a call, right. If we think that our model is satisfactory, then we deploy. So deployment can take various forms. So if it is scientific research, then you typically try to publish the model, make it available to other researchers. If it is industry, then you deploy it for commercial purposes. So maybe you sell this model to your clients, you use this model to make for decisions on your manufacturing, processing pipelines and so on, right. So you decide how to deploy the model, right. So let us look at our evaluation, and let us go back to our notebook, right. So the evaluation is fairly straightforward. So we take in the best model that we got from our grid search CV. So we take the best random forest model, and then we basically we have the test data, all the unprocessed data. So from the test data, we make sure that we drop the target values, right, which are our median house values. We assign them as our target labels, right. So that is why we define X test and Y test here, right. So X test is unprepared data, so we have to prepare it. So we prepare it using our pipeline. So we use our full pipeline, which does both numerical attributes as well as categorical attributes, right. So we transform using our full pipeline to get the fully prepared data, right, and then we make predictions, right. So the final predictions, we basically take our final model, our best model, right, and then use predict with our finally prepared features, X test prepared, right. So that gives us our final predictions. Now we can evaluate our error metrics, right. So we can evaluate our mean squared error, right, our Y test are our target values, our true values, our final predictions are our predicted values, right. So we evaluate mean squared error and then take the square root to get the root mean squared error, and then let us see what the root mean squared error is, and looks like it's fairly okay. So if you take the random forest model, you get a root mean squared error on your test data set of about $47,000, right. Remember that the best random forest model with our cross validation errors had an error of about $49,000 on our training set. So on our test set it has an error of about $47,000, so the errors are comparable, which implies the model is actually pretty decent, right. So it is doing a good job of learning from the test set. It is able to make reasonable predictions on our it is able to learn trends from our training set, and it is able to make reasonable predictions on our test set as well. So the model is not overfit or anything like that, it is able to make predictions, and whether this error value $47,000 is good enough or not, that is a decision that we have to take. Now we may conclude that this value is not good enough, we need higher accuracies, which means we may have to increase the complexity of our models, or we may have to increase the amount of data that we have, we may have to collect more data. So in many instances data collection may not be in our hands, so we may have to explore increasing complexities. So we could go into more black box type models such as neural networks and so on, right. So that could help us improve the models, but otherwise this is the best model that we have, right, so far. And we can also compute the confidence intervals for these models. So what is the error bar in our predictions, right. So let's say you evaluate 100 different models, what will be the range of errors, root mean squared errors in 95% of the models, and that is what this confidence interval gives you. So you see that the 95% confidence interval is between $45,000 to about $49,000. So within that range your model will make errors, the root mean squared errors will vary in that range, right. So we have evaluated our model, and we have actually completed a very rigorous set of regression exercises. So, congratulations, you already know quite a bit of machine learning, right. Let us get back to our slides and let us summarize what we have learnt in this lecture. So, we started off with defining a regression problem which is predicting median house prices in California. We had to put in quite a bit of effort to prepare the data. We did imputing, one hot encoding, adding new features, and we also did standardization, right, and we put everything in the form of transformers and pipelines, and then we fit the models, we evaluated the models on the training set and using cross validation, and we did some hyperparameter optimization for our random forest model. We found the best model using grid search CV. There is also the process of randomized CV, but we chose the best model with our grid search. And then we finally evaluated our model on the test set that the model has not seen completely, and we see that our best model performs equally well on both the training set as well as the test set, right. So, with this we have completed our regression workflow. In the next lecture we look at how typical workflows look like for classification problems. So, with that thanks for joining today, and I will see you all in the next lecture.